Okay, I want you to picture a tadpole, but not just any tadpole. I want you to picture what scientists call a Picasso tadpole.
A Picasso tadpole. Okay, what is
Yeah,
that?
literally. Imagine scientists taking a developing frog embryo,
Uh,
just treating it like a Mr. Potato Head. They scramble the face.
Scramble it how?
They put an eye on its tail.
Yeah.
The mouth ends up on the side of its head. The other eye is somewhere down by the spine. It's a complete biological mess.
That sounds like a broken machine. I mean, if you did that to a car, put the steering wheel in the trunk, it's just game over.
Exactly. That's what our intuition says. The blueprint is ruined, right?
Yeah.
But here's the crazy part. As that tadpole grows, the parts, they start to move.
Move.
The eye on the tail migrates. The jaw shifts. The mouth slides around. And by the time it turns into a frog, it is a perfectly normal, symmetrical frog face.
It creates order out of what should be total chaos.
But how? That is the question that I swear keeps me up at night. The cells in the tail don't have a hard-coded instruction that says, if you find yourself here, walk 3 inches northwest. The map was completely wrong. So how did the system know where to go?
And that is the absolute mystery we're unpacking today. We're looking at a paper called Remapping and Navigation of an Embedding Space via Error Minimization.
It's by a really heavy-hitting team, Benedict Hartle, Leo Pio Lopez, Chris Fields, and the biologist Michael Levin.
And their mission here is huge. They're not just trying to explain weird frogs.
No, not at all.
They're proposing a kind of unified theory of intelligence. They're arguing that the rule bringing that tadpole face together is the exact same mathematical rule that lets an AI write a sonnet or generate an image of a cat.
So we're connecting the squishy, wet biology of a frog to the dry, silicon world of artificial intelligence.
We are. And it all hinges on these two massive concepts, remapping and navigation.
Okay, let's get into the weeds then. Because usually when I hear intelligence, I'm thinking about a human brain, right? Solving calculus, playing chess. But this paper seems to want to throw that definition out.
Not throw it out, but expand it radically. The authors take what's called an operationalist view.
An operationalist view.
Basically, they argue intelligence isn't about what you're made of. It doesn't matter if it's neurons or silicon chips or even a chemical soup. Intelligence is defined by how you behave.
So if it acts smart, it is smart.
Precisely. They lean on a great definition from the psychologist William James. He said, intelligence is a fixed goal with variable means of achieving it.
Fixed goal, variable needs. Okay, let me ground that. My goal is get coffee. That's fixed.
Yeah.
But the front door is locked, so I climb out the window. That's a variable mean.
Exactly. And if the window is stuck, you might try to pick the lock. You navigate the obstacle. You don't just walk into the lock doing it over and over again like a broken robot.
I feel like I've seen my robotic vacuum do exactly that.
And that's the difference. Intelligence is that ability to navigate around the problem. And this paper argues that this ability isn't just a human thing. It exists at all scales.
All scale.
We see it in ion channels in your cells, which existed billions of years before brains. Individual cells are what the authors call competent agents.
Competent agents. That makes them sound like tiny employees.
In a way, they are. They solve problems in their own little worlds.
Okay, but wait, this is where I get a little stuck. When I solve a problem, like getting that coffee, I'm moving around in the real world, 3D space. But a single cell in my liver, it isn't going anywhere. What space is it navigating?
That is the million-dollar question, and this is the first pillar of their theory, problem spaces.
Problem space.
So we're addicted to 3D space because that's where our bodies live. But a cell, it doesn't care about north or south. It lives in, for example, metabolic space.
Metabolic space.
Yeah, imagine a landscape with hills and valleys. But instead of latitude and longitude, the coordinates are things like sugar level, acidity, protein concentration.
So it's like a graph.
It's a multidimensional graph, yes. The cell is currently in a spot where the acidity is too high. That's a bad location. It's in a valley of death. It needs to get to the healthy peak. So it opens an ion channel or burns some energy. That action moves it to a new coordinate on that graph.
It's navigating, just not a city map.
It's treating chemistry like geography. And
Yeah.
once you get that, you can understand the wildest example in this entire paper, the planaria.
The flatworm, the superstar of regeneration from high school biology.
Basically immortal. You can cut them into tiny pieces, and each piece will regrow a whole new worm. But this paper talks about an experiment with barium that it completely changes how we view evolution.
Barium, that's a heavy metal, right?
Right. And for a worm, it's a neurotoxin. It blocks its potassium channels. In plain English, it shuts down the cell's ability to regulate themselves.
So the researchers drop these worms, which usually live in fresh water, into a barium solution. What happened?
It's pretty grim. Their heads literally degenerate. They melt away because the barium destroys their ability to maintain that head shape.
Okay, sounds like the end of the story. The machine broke.
You would think so,
Hmm.
but if you leave them in the barium, they don't die. Over a few days, they regenerate new heads.
Whoa.
And here's the twist. These new heads are different. They have completely rewired their gene expression to be resistant to barium.
Hold on. I want to pause here because that's insane. Evolution works over millions of years. Random mutation. These worms have never seen barium in the wild. There's no anti-barium gene just sitting there.
That is the aha moment. Evolution could not have prepared them for this. If they were just hard-coded robots executing a script, they would have died. The code would have crashed.
So how did they do it?
They navigated what's called transcriptional space. Think of the genome not as a fixed instruction manual, but as a vast library of possibilities, a huge switchboard. The cells realized the current settings were leading to death.
So they just started flipping switches.
They started searching, navigating through thousands of possible gene combinations, moving through that abstract space until they found a location that allowed them to survive.
Okay, it's like I'm in the cockpit of a plane I've never flown, the controls are in a language I don't speak, and we're nosediving. I don't give up. I start flipping switches, testing things, trying to stabilize the plane.
And you do it fast enough to not crash. That is exactly what the worm did. It remapped its internal survival guide on the fly. And get this, once they figure it out, they remember, if you cut those new heads off, the next heads they grow are also barium resistant.
They updated the map permanently.
They updated the map. And this brings us right back to your Picasso tadpole.
Right, because the tadpole cells didn't have a rigid instruction like move 2 millimeters left.
Correct. If they did, starting the eye on the tail would just move it slightly further up the tail. The system doesn't have a rigid path. It has a target morphology.
It knows what the destination is supposed to look like.
In physics, they'd call it an attractor. Think of a marble in a bowl. No matter where you drop that marble on the rim, it eventually rolls to the bottom. The normal frog face is the bottom of that bowl. The cells are just the marble navigating the landscape to get there.
So when the scientists scrambled the face, they just dropped the marble in a really weird spot on the rim of the bowl.
And the biology just went recalculating. That is the core idea. Intelligence is the ability to navigate abstract spaces to reach a goal, even when the starting point is all wrong.
There's another visual in the paper that shows this so well. The deer antlers.
Yes, the Siberian wapiti in Figure 1.
Right, so it shows this antler, and there's an injury. Something damaged it while it was growing, and the next year, when the deer grew a new set, what happened?
It grew an ectopic tine, an abnormal branch, right where the injury had been. The trauma actually altered the target morphology. The system's map of what an antler looks like was changed by the injury.
So the memory of the injury wasn't just a scar, it became part of the blueprint.
Exactly. And this idea, remapping a blueprint based on new data, is the perfect bridge to talk about the other half of this paper, artificial intelligence.
Right, because I look at a flatworm, and then I look at ChatGPT or Midjourney, and they see nothing alike. One is wet and squishy, the other is servers and code.
On the surface, sure. But the authors claim they're doing the exact same thing, and the key to that connection is a concept called embeddings.
I hear this word all the time in AI circles. Vector embeddings, latent space. Break it down for me. What is an embedding, really?
So the paper defines it as mapping complex data into a lower dimensional space where distance equals meaning.
Okay, textbook definition. Give me the simple version. Distance equals meaning.
Okay, think about words. To a computer, king is just K-I-N-G, meaningless. An embedding model turns that word into a long list of numbers, a vector. And that vector is a coordinate in a massive multidimensional space.
A coordinate, like a point on a map.
Exactly. A huge map of concepts. And on this map, words with similar meanings are close together. Cat is practically neighbors with dog. They're in the pet neighborhood. But cat is miles away from carburetor.
So the computer knows they're related because they're close on the map.
Yes, but it's more than that. It's geometry. You can do math with them. The classic example, which is in the paper, is if you take the vector for king, subtract the vector for man, and add the vector for woman, you land almost exactly on the vector for queen.
King minus man plus woman equals queen. That's honestly deeply satisfying.
It's geometry. Meaning has a shape. And this is where the connection to the worm comes in. Just like the worm navigates gene space, and AI navigates meaning space.
So when I talk to a chatbot, it's not just looking up a response in a database.
No, not at all. It's taking your words, turning them into coordinates on this map, and navigating to the next most likely coordinate. But the crucial part, and this is with models like ChatGPT, is they don't use a static map. They use what are called attention mechanisms.
Attention. That's how they focus on certain words.
It's how they understand context. If I say bank, do I mean a river bank or a money bank?
Right.
The model looks at the other words, and it shifts the meaning of bank. It updates the coordinate. It remaps the space on the fly.
Just like the planaria remapped its gene space when it hit the barium.
Precisely. The conversation history is the new environment. As the conversation changes, the AI updates its internal map of what the words mean.
But the paper argues the strongest link isn't the chatbots. It's the image generators, diffusion models.
This is my favorite part of the paper. Because the parallel is almost spooky, think about how a diffusion model works. It starts with pure static, noise.
Yeah, it looks like old TV with no signal.
And then, step by step, it denoises it. It removes the static, finds patterns, refines them, until, boom, you have a photorealistic cat.
It's navigating from chaos to order.
Now think about an embryo. It starts as a single fertilized egg. That's a state of high potential, high entropy. And then, step by step, it divides, it differentiates, it refines itself until, boom, you have a complex organism. The paper argues that morphogenesis, the creation of a body, is a denoising process.
That is a beautiful image. The embryo is denoising itself into existence.
And they actually compare the two processes side by side in Figure 4 of the paper. With the AI, you're navigating from a noisy vector to a clean image vector. With biology, the system is navigating from a single cell to a target morphology, that face we talked about. They're both finding an attractor in the chaos.
So let's recap the mechanics. Remapping is drawing the map. Navigation is driving the car.
Yeah.
But what's the fuel? What makes the tadpole actually move instead of just staying scrambled?
The engine, according to the authors, is error minimization.
Error minimization. It sounds a little dry for the force that drives all of life.
It might sound dry, but it's incredibly powerful. It's also called active inference. And here's the loop. The system, a cell or an AI, has a prediction. It expects its world to be in a certain state.
Okay. So for the tadpole cells, the prediction is we should form a face.
Then comes perception. It looks at the current state. Wait a minute. The eye is on the tail.
Perception. Total mess.
Right. And the difference between the prediction and the perception is the error. The system is fundamentally driven to reduce that error. It moves the cells until the perception matches the prediction.
It closes the gap. My head is cut off is a massive error signal for the worm. Regrow the head minimizes that error.
Exactly. And this applies to the AI too. The diffusion model predicts what a cat should look like, sees the static, and subtracts the noise to minimize the difference.
The paper mentions a specific AI called NCA's Neural Cellular Automata that seems to literally embody this.
Yes, NCAs are fascinating. They're a perfect bridge. Imagine an image where every single pixel is a little agent, a little cell. And that pixel can only talk to its immediate neighbors.
It has no idea what the whole picture looks like.
None. But they're all trained to minimize error collectively. So if you go in and delete a chunk of the image...
The neighbors notice, hey, my neighbor is gone. That's an error.
Exactly. And they communicate to regrow the missing part. NCAs can literally regenerate parts of an image, just like the planaria regenerates.
Weird.
It shows how local agents, cells, or pixels can build a global structure just by talking to their neighbors.
So there's no general commanding the army, just soldiers talking to the guy next to them.
Precisely. And this all leads to the big final concept in the paper, the multi-scale competency architecture.
Multi-scale competency. Sounds a bit like corporate buzzword bingo.
It does, but it's really a nesting doll concept. Biology isn't one intelligent thing. It's intelligence nested inside of intelligence.
Walk me through the layers.
Okay, at the very bottom, you have molecules navigating chemical space to keep a cell alive. Then you have cells navigating transcriptional space to keep a tissue alive. Above them, organs navigate morphospace to keep the whole animal alive. And finally, the whole animal you navigate's 3D space.
And each level is remapping and navigating its own little world.
Correct. But here's the trick. The higher levels set the goals for the lower levels. The animal says, I need to run from this tiger. That command changes the chemical landscape for all the cells, forcing them to burn energy. The big map distorts all the little maps.
I am just the top-level goal setter for trillions of lower-level agents.
And those agents are intelligent. They are not just dumb gears. They are actively navigating the problems you give them.
Okay, let's step back. We've gone from Picasso tadpoles to barium-resistant worms, king-man math, and embryos as image generators. What does this all mean? Why does this paper matter?
It matters because it moves us away from what Michael Levin calls brain-centric chauvinism.
Brain chauvinism. I like that. The idea that only brains matter.
Right. We tend to think if it doesn't have neurons, it can't think. But this paper shows that the mechanisms of thought remapping, navigation, error minimization are universal. They're in our cells. They're in our genes.
And for AI, this seems to have huge implications for how we actually build this stuff.
This is the critical takeaway. Right now, we build most AI by just feeding it massive amounts of data. But if we want AI that's truly robust AI, that can fix itself, that can adapt to totally new problems like a planaria did, we need to look at biology. We need to build systems that act more like embryos, not just calculators.
We need AI that can function when its face is scrambled.
Exactly. We need systems that can function at what the paper calls criticality, that edge between order and chaos. That's where a system is most adaptable. If you're too rigid, like a crystal, you break. If you're too chaotic, like a gas, you just dissolve. Life surfs that edge.
Which leaves me with a thought that's been nagging me this whole time. If my cells are intelligent and my organs are intelligent, then who am I?
That is the provocative final thought, isn't it? The paper suggests that our consciousness, that voice in your head right now, might just be the macro version of a single cell trying to minimize its own error. You feel like a unified self, but maybe you're just the collective goal of trillions of tiny agents all navigating their own spaces.
Am I the captain of the ship, or am I just the collective hum of the entire crew working together?
Or maybe the ship, the crew, and the captain are all just different ways of looking at the same map.
On that dizzying note, we're going to wrap up this deep dive. Navigating the space between biology and AI is a wild ride, but hopefully we've minimized your error just a little bit today.
Keep remapping your worlds, everyone.
Thanks for listening. We'll see you in the next deep dive.